Hi guys, and welcome again to my channel. This should be episode 10, and we're going to be looking at quantum chemistry. Now, before we start, I'd like to say quantum chemistry is a vast topic. You'd love to look into it thoroughly. It's pretty profound. You'd love and enjoy studying it. Now, what I'd say is there's a lot that goes into it. There's a lot of chemistry and a lot of technical topics and subjects involved. So I would implore you to go and refer. The more you study it, the more you'll be better at it. Now, without further ado, let's go right into it. So, everything is made of atoms, and atoms are made of core, which are the nucleus, and electrons. So, depending on different protons, you can get elements, right? So, quantum mechanics tells us that the atoms look a bit different. Yeah, according to quantum mechanics, the atoms are not actually shaped the way we think, like Saturn or like an atom with, like, what are they called? Electrons rotating around it. It's mostly like a DNA ball, which involves different parts. But anyway, let's continue. So valencies are Saturn rings in an atom. Elements with same valencies and electrons tend to show similar behavior in chemical reactions. That's referencing the periodic table. Different elements with the same valencies usually behave similar in different reactions, chemical reactions. So in the periodic table, different elements increase in shells from left to right, gaining protons and electrons. Now we studied this in the periodic table, the way the metals and all of those reacting elements usually behave. So giving different isotopes which fall apart releasing ionic radiations, right? So charged atoms are called ions, negative are called ions, right? Semi-atoms at the center of the table semi-atoms at the center of the table. So the Lewis dot structure shows the structure of an atom and shows how they bond. This is a technique used to measure and show how reactions in certain elements. We'll see that in the coming future. So it shows the structure of an atom and shows how they bond. Sharing of electrons is a covalent bond. Electronegativity, the pull of the atoms, right? So far we are discussing how elements react. We can see like something like sodium, which is Na, and chlorine, which is Cl, how they bond, they share atoms, and when they come together they share atom and like, right? Okay. Ionic bonds, is the difference is 1.7. Let's just continue. This usually happens in salt. A lot of these elements that we're looking at are usually salts, and what you don't know is the normal table salt we usually use is definitely one of these reactions, right? There's a lot that goes into it, but if you study it, you'd see that salt is one of the byproducts of these chemical reactions we're talking about and this bonding. Okay. So freely moving electrons, valence electrons, they are promiscuous, right? In the periodic table, the elements which lose electrons pretty easily. That's why they say they're promiscuous, because in the end you'll see like an atom just leaves, right, and goes and bonds and reacts with another one. Like, not reacts, like bonds, right? This is malleable. They say it's called malleable. So polar covalent bonds trying to steal a bond until it ruins into shapes. So some of these bonds, they try to like bond together, but sometimes one of them is like more aggressive, and it just goes like pam pam pam, then pam, and then until this one is broken, right? And this one gets it. Okay. So yeah, that's quantum chemistry so far. Let's continue. Intermolecular forces, IMF, for example, are hydrogen bonds and they are electronegative. Is this the one that we were talking about? Intermolecular forces, if I'm not mistaken, is when you need, it's when you need like that's a different one. So IMF is like hydrogen bonds and they're electronegative. That's different, right? You can call them IMFs. They're called IMFs. So van der Waals forces, H2O, like water, does not dissolve non-polar molecules, for example H2NO. So van der Waals forces is when water, it does not react with the elements, like it doesn't just react, it just doesn't. Like, that's the case of oil and water. It's called van der Waals forces, right? So soap works with a polar head and a non-polar tail, states of matter in solid. So soap, yeah, you get that one. So in quantum chemistry, we also look at entropy, the temperature. No, not. We look at the states of matter, like solids, liquids, and water. So in there we also look at temperature, for example ice into water, and the entropy involved, right? So milk is called colloid, and how it mixes with H2O. Now, how water and milk mix is like, they just mix, yeah, but the way milk operates, the bonds usually spread uniformly across the water and they do not lose themselves. So you'd find like milk is there and there's water, but if you take a closer look, you can find that the elements are still spread out perfectly. This is why we call them colloids. So stoichiochemistry is where you meet twice as much of one electron. Stoichiochemistry, that's when you need like 2 for 1, right? Yeah, exactly. In water, that's stoichiochemistry. You need like 2 hydrogen atoms for 1 oxygen atom for in water. That's stoichiochemistry. Endo and exothermic reactions are also covered in quantum chemistry. We've seen it before, but yeah, they fall under quantum chemistry. So we also look at another phenomenon called Gibbs free energy, which is the loss of energy based on the 0 point. So far, I get that one. There's just, it's like exo and endothermic. It's entropy, based on the reaction is based on like temperature. Like if it goes below 0, yeah, you get that stuff anyway. So we also look at Bronsted and Larry. That theory says that bases and acid receiving and donating protons and electrons. But if you've been following this channel, you know exactly what we're talking about. Uh, so receiving and donating protons and electrons. We've covered that before. Reduction of oxidation reactions are giving and losing electrons, right? It's called reduction oxidation. It's the same principle of Bronsted and Larry they covered. This is sodium and chlorine. We've discussed that reaction. The giving and losing of electrons, which also gets us to cover oxidation numbers. So quantum numbers include N, L, Ml, and Ms. N considers the shells and subshells inside them, and Schrödinger covered N is shells and the subshells inside them. Schrödinger discussed this matter. L is the shape and Ml is the subshape. If L and Ml are together, it's considered the same orbitals. Ms is considered the spin, within the electrons. So Bohr principle is the number n that are different. Like Bohr principle looks at some of these numbers. For example, they are 3p, 4s, 4p, 4d, and the difference in the periodic table. The difference is when the periodic table, like, because the atoms are different, the numbers become different. Like, yeah, you check the periodic table closely and you see that the numbers are like 1.00, like 2 point, and so that gives out the principle that 3p, 4s, 4p, yeah. So valencies can be found by this method. Yeah, you can find the valencies using the Bohr principle, the numbers, right? It's a great way to calculate them, the valencies. So that was quantum chemistry in a nutshell. That was what 10-12 minutes. I know you haven't gotten it properly. There's so much we can do on our channel to actually explain some of these principles properly. We need a pie chart to show you these things. So that's why, as a teacher dabbling in this chemistry world, I'd implore you to go and sharpen your mind and let these teachings and these videos make you brighter in such matters. Yeah, let them motivate you to go and refer to them in the internet. So that was episode 10. I hope you enjoyed it. Peace.